Guys, again, you see what you see here, these are compound cylinders. These are compound cylinders, okay? So what I can tell you is when you take this cylinder, you join it with this cylinder, it becomes it becomes compound cylinder, which is two thick cylinders. When they are joined together, they become a compound cylinder, okay? So now what I want to tell you is you must move in this order. The formula is provided for you. You must first start with you can start analyzing, which at this point I'm analyzing the interface pressure, which is PO. Usually is given as it's a pressure that is acting due to shrinkage. When you are shrinking the cylinder, which is when you take one cylinder, you put it inside the other one is going to be shrinked, and the other one is going to exert a force on the outer diameter of that cylinder, which is the cylinder that you put it through the other cylinder. They're going to have what you call is remember that the forces, they must be equal in opposite. So which is what we see when we're looking at this and at this. So this is PO, but it's acting in opposite. So it's affecting these two cylinders, which is inner cylinder and the outer cylinders, differently. So now what we're interested in this chapter is you want to find how much does the stress it changes as you're moving towards a certain rate or a certain point. Let's say now we're moving towards inner radius. So now we're going to analyze each and every radius. So we're going to start at the outer radius. At the outer radius, we know that this is PO that is acting, which is the interface pressure, which is the radial stress at that point. So we are interested in the next step in finding what is the circumferential stress, because they must coexist. These two things, they exist. One cannot exist without the other. It can be zero, or we want to find what is this one. But the circumferential stress cannot be zero. A radial stress can be zero at some point. For instance, on the outer cylinder, it could be zero because there is no force that is acting. If they say there is no pressure that is acting at that point, to assume atmospheric pressure. Okay, so now starting from out, we're gonna find what is the circumferential stress at this point. We know what is PO, and then you move from there, you go to the mean radius one, which is the main radius one. It exists between the two radiuses, which is the one that is inside and the one that is outside. So the average between them is the main radius, which is you're gonna sum the two and you divide by two, and then you get that main radius. And then you move to the main radius, you analyze that point. What is the radial stress at that point? What is the circumferential stress at that point? Remember that these circumferential and radial stresses are also influenced by this PO. So it's the effect of shrinkage that we want to understand. How does this stress changes as you're moving towards a certain point? If you're moving inside, you're going to analyze moving inside or moving outside. Same wise as when you have the internal pressure. When it's the internal pressure, it acts inside the whole cylinder. Now the cylinder has to be one cylinder, but in your mind you must know this, that even though I picture it as a complete one cylinder, but this complete one cylinder, it is made up of two thick cylinders. So now you need to go to cylinder by cylinder, cylinder by cylinder, cylinder by cylinder. So in inner cylinder, in analyzing that one, you're gonna say that okay, in the inner cylinder, the radial stress must be equals to the P internal, which is the internal pressure, the pressure that is due to the fluid that is moving inside, or to the air that is going or is moving or is pressured inside. Okay, so that is the internal pressure. So think of a condom. I usually tell people that if you think of a condom, you take a condom, you put inside the other, and then you blow inside. So they're going to expand together. So think of that thing as one condom that is being fitted inside the other, and then you blow it, and then the effect is going to affect the whole thing, which is compound cylinder now. Okay, so you're gonna move from inside, which is the inside. You're gonna find what is the internal pressure. The internal pressure, which is the radial stress, which is going to be equals to Pi, and then that Pi, which is which is a pressure, internal pressure, this one, which is now we're gonna go to the next step. What is the circumferential stress or dimensional stress at that point, which is at inner radius, you find, and then you move to the second radius, which is the second radius is the main radius between the common and the inner, and then this one inside, this one dotted inside, which is this one dotted. Yeah, you must find at that point. So there must be two stresses in each and every point you analyze: circumferential, radial. Okay, thank you. Okay, guys, welcome again. Namhlanje ndizanifundisa ukusolva i-compound cylinders, ne? So I hope you're going to see what I'm doing. So sorry. So focus, keep on focusing. So if you don't understand anything which is to do with the applied strength of materials, I think you can contact me anytime. We're gonna do this thing together, and then I'm going to see where I can help you so that you can catch up. Okay, so now let's go ahead to define everything. So this is a compound cylinder. Let me add one more layer now. Okay, sharp. Okay, so that you can see. So you can see. Don't mind that it's not straight or what, but you're going to understand that application, So let's follow the application, guys, and not mind what you see there. So I'll assume that our interface pressure is 4 megapascal and our internal pressure is 33 megapascal. So now okay, so we're gonna define again the radius is now okay, so we're going to define the inner radius, which is 25 millimeter, and the common radius, which is defined as RO, is 45 millimeter, and the outer radius, which is R2, must be 65 millimeters. Okay, so considering the inner side, the inner cylinder. The inner cylinder will be subjected to the compressive stress due to interface pressure. So the outer cylinder is compressing the inner cylinder. So we are going to try and understand that effect and then calculate the magnitude of the stresses that are induced in these bodies, especially in the inner cylinder and its radiuses. So we're going to go ahead and understand how these stresses varies from that interface or common radius to the inner radius. Remember that at the inner radius, the radial stress is completely zero. There we only have the circumferential stress or the diametral stress. So the stress that goes around it's more like it's trying to in the inside. Obviously it's going to try to squeeze this thing all around the surface, you see. So we call it circumferential stress, that one, because it acts on the circumference of the cylinder. So what we are going to do now, we are going to try and understand how these stresses varies as you go to the inner. So now we know that our radial stress is going to be 4 megapascal, okay, because it's given as pressure that is due to shrinkage, okay. So at R1, as I told you, that the radial is 0. So now we're going to need to look at the RO. We want to find what is the circumferential stress at that point. So at that point, we know that it's going to be given by this formula I'm giving you. What governs us is the pressure at that area and the radius at that area. So you're going to have to understand your formula very well so that you don't make mistake, okay. So this is a standard formula for calculating the circumferential stress that is acting at that point. So yeah, so you can see most, you're gonna punch the calculator and then you find what is x. The x is the correct value. So I'm just giving you the procedure here. This is what you need to follow when you're solving such situation or such problems. You just follow what I'm doing, okay. And then your x is going to be your actual answer, right? Okay, cool. So remember, there's this formula that says radial stress plus circumferential stress must be equal to 2a, which is a is the constant. When you read your notes, you're going to know what is a. So okay, because we already know what is radial stress at outer and the circumferential stress at outer, we can find what is 2a. So if you want to find 2a is going to make things easy for you, that constant, because you can find one stress and then the other one you can just find in this using this formula, okay. So this is another way of solving when you already know one and then you want to find the other, okay. So I'm gonna write it in terms of x so that you can find what is x, and then you substitute there and then you find what is 2a, or yeah. And then do not solve for a, just leave it as 2a, because the formula, it says sigma r plus sigma c is equals to 2a, okay. All right, so now at another radius, which is we're gonna move with respect to radiuses. So now we're moving to rm, which is rm1, which is mean radius 1. Okay, so now at rm1, we know that at rm1 is going to be x millimeters. So now we're gonna have to find what is that x. So I don't want to solve, I just want to give you a procedure on how to do these things. I'm not gonna be solving, guys, so it's just a procedure, a way of doing this thing. So this thing is going to be the same for the rest of the cylinders, so it does not change, guys. So I'm not going to spend much time explaining, so you just follow what I'm doing and then you put the right answer, the right values, and then you calculate your answers, okay. And then okay, so remember that we found what is a there above. So now remember that 2a is equals to x plus minus 4 megapascal is equals to, okay, is equals to whatever that thing a is there, 2a. So when we found this radial stress at this point, now you can find what is the circumferential stress using that 2A is equal to, so minus is going to be minus what radial stress of this one, which is on this part there. Okay, so you can find using that formula your circumferential, and then you move now. Yeah, so the same thing is gonna apply to the other radiuses, all the radiuses. It's gonna be the same procedure. And then now we can move and go find the other radiuses, which is now we can focus on the outer cylinder now. Okay, we are going to focus on the outer cylinder. On this outer cylinder, remember that the procedure is the same, just that now we have to look at the pressure that is acting in the interface faces. Okay, so we call it the interface pressure. You're gonna have to focus on the pressure that is acting there on the interfaces, which is on the common radius. So it's acting like that on the outer one. So when you try, it's called action and reaction. If the other one is trying to squeeze, and then in opposite, the forces or the stresses, they must be equal in opposite. So our PO, okay, so these are our radiuses. I'm defining our radiuses, which is now arrow. Remember now arrow, it acts as an inner radius now. Okay, because we're focusing on the outer cylinder. Okay, so also the procedure is the same. Radial stress at outer cylinder, which is at 2, there is no atmospheric pressure there, we assume. So we know the radial stress at that point is 0, which is at R2. P is equals to 4 megapascal. PO. Okay, now that at R2, we are analyzing at R2, but now analyzing with respect to PO. So at R2, PO is not 4 megapascal. Just as I'm telling you, I'm analyzing using this PO, which is the interface pressure. So we already know that what you see is going to be 2A. Now we need to find what is going to be 2A. So we're going to find what is 2C there first, which is looking at PO RO squared. We still are using that. So now it's R2, no longer R1. So instead of R1, we change it to R2 because we are looking with respect to outer radius now. Okay, so that's R2 over R2 squared, which is going to be 1 plus 1, it's 2. So we're looking at the outer cylinder now. We are more concerned about at R2, at outer cylinder. So it's equal to 2. Whatever that is inside that bracket is equal to 2, because it's going to divide what R2 divided by R2, it's 1 plus 1, so it's 2. So now we're gonna have our so now remember the same thing that we did on the previous one is the same until you get to the outer radius, which is we started on the outer radius here. Now we know that on the outer radius we have no radial stress there, it's 0. So now we can work towards the inner radius, which is towards PO. When you get to inside, which is at RO, you will find that our radial stress, even if you use your calculator, will find out our radial stress is it's already given by PO, which is equals to 4 megapascal. So you're gonna find that even if you punch it on your calculator, you're still gonna get to that 4 megapascal acting inside. Okay, so hence I'm saying that you're gonna do the same thing as we did on the inner cylinder, and then now so when you focus on which is the third step, is to focus on the whole cylinder now being affected by the pressure that is inside, which is, I usually tell people that think of a condom. But it's easy to think of a condom because I like the condom fact that it is transparent. You can put another condom inside and then you blow the one that is inside the other. You're gonna see that when you blow the condom that is inside the other, what happens is that although you did not blow the outer one, they're going to expand at the same rate. So now what I'm saying is, if you blow the inside, it's going to affect the outside the same way. Okay, so the visual example is of taking 2 condoms and then put one inside the other and then you start blowing, even if you put 3 of them, but because it's 2 cylinders that are thick and then being combined together, and then they put a pressure inside. So that pressure that is inside, regardless if it is applied to what to where inside, but it's going to make the whole thing expand. So yeah, and then now we are going to do the same thing on this one. You see what we did above, we're still gonna do it here, because we started now we're gonna have to start at a certain radius. If we start at R1, we're gonna start at R1 and then we move to all the radiuses. We start at R1, you're going to, if you move from R1, you know that after R1 it's going to be what? At R1 we must find 2. At RM1, which is at R min radius 1, you must find 2 stresses at that point, and then you go to the common radius, you find 2 stresses at that point, and then you go to the RM2, which is the main radius 2, and then you find the same thing like that you're going to do for the others, which is you find 2 stresses at each and every radius. You must find 2 stresses. If you know you're working in that order, you will know that you're not going to have one we must have pair of stresses, which is circumferential or circumferential stress and the radial stress. So we are looking for the 2 stresses, radial and circumferential at each and every radius. Okay, so if you start at R1, you're gonna see that at R1 we have P in, which is 33 megapascal. So at R1, you already know that you have your radial stresses. That now you need to find what is your circumferential stress, which is sigma C. And then you remember we have a formula of 2A is equals to radial stress and circumferential stress, and then you can use that relationship as well to get the other stress in terms of the other. So this thing is very fun when you understand that you must move in a certain order, and you must make sure that for each and every radius you analyze, you get the 2 stresses. 2 stresses, okay? So you want at RM1, you must find what is the radial stress at that point, which is you're gonna use the formula. Formula is there for you, that takes care of everything, okay? But remember the catch is somewhere here, you see, because you're analyzing RM now, you must make sure that you don't change that R to there above. You change only what is below, which is RM. So and so on, okay? So you do the same thing until you